Combinatorial miRNA1A/15B interference drives adult cardiac regeneration. Preprint by Yuan et al. Presentation by Kate Crotty. Heart failure remains a major cause of death globally. Loss of cardiomyocytes is a primary indicator of heart failure in congenital age and stress-related heart failure. Cardiomyocytes have negligible capacity for proliferation, regeneration, or the ability to restore damaged tissues, which leads to heart failure. Cardiomyocytes exit the cell cycle and cease proliferation in the early postnatal period. Gene therapies have been used in recent years to help proliferation, but have various degrees of success. These attempts tend to have a complex and invasive delivery which has limited the accessibility for patients. Another concern is that previous studies have indicated that proliferation induction of adult cardiomyocytes requires coordinated regulation of multiple genes to overcome the barriers to re-enter the cell cycle and engage in mitotic completion. In this paper, the researchers used microRNAs, which are a small non-coding RNA that promotes mRNA degradation and translational inhibition. They have been shown to play key roles in heart disease development and the progression to heart failure. miRNAs function by regulating key genes involved in proliferation, inflammation, and metabolic reprogramming. Many ongoing trials looking at this topic have focused on modulating disease-linked miRNAs in heart disease. In this paper, the authors decided to use a combinatorial RNA interference strategy, which means they used more than one miRNA in their experiment. They decided upon this after finding that single miRNAs could not robustly modulate all relevant pathways. This type of strategy has not been explored much in heart disease, but has been noted to be very successful in antiviral and cancer therapy. In antiviral and cancer therapy, combinatorial targeting of multiple genes has been seen to better overcome phenotypic and genomic evolution to increase therapeutic robustness and efficacy. The key question the researchers were assessing was the need for novel therapeutics to enhance cardiomyocyte regeneration and reduce the morbidity and mortality from heart failure. They put a focus on the need to simultaneously modulate multiple pathways to induce physiologically relevant proliferative rates. Additionally, they wanted to determine if a combinatorial RNA interference strategy would provide the necessary reprogramming for adult cardiomyocyte cell cycle reentry and mitotic completion. They created this goal after they were not able to identify single miRNAs that were capable of robustly modulating all relevant pro-proliferative pathways in cardiomyocytes. Novel therapeutic strategy for adult cardiomyocyte regeneration. Specifically, the authors wanted to demonstrate that combinatorial miRNA interference using locked nucleic acid anti-MIRs with MIR1A and MIR15B can drive adult cardiomyocyte cell cycle reentry, enhance proliferation, and improve heart function after myocardial damage. The researchers also had a sub-goal of trying to find feasible and safe regenerative therapy for heart failure by reprogramming multiple pathways that restrict cardiomyocyte proliferation. For choosing of the miRNAs, in silico expression and pathway connectivity analysis were performed to independently identify miRNAs expressed in the heart with the capacity to modulate pro-proliferative pathways in cardiomyocytes. From this analysis, 17 miRNAs were identified. A novel combinatorial RNAi screening was used where the effects of a single miRNA interference was compared on the background of interference of all other miRNAs. The researchers tested the physiological relevance and efficacy of combinatorial inhibition of MIR1A and MIR15B in driving cardiac regeneration in mice subjected to myocardial infarction. They found that MIR1A and MIR15B interference with locked nucleic acid and anti-MIRs significantly augmented cardiomyocyte proliferation, which could be seen through EDU incorporation and Aurora B localization in newly adult daughter cardiomyocytes. In Figure 1b, it can be seen that LNA MIR1A and LNA MIR15B stand out with the strongest increases compared to negative control, and that many other miRNAs show minimal or inconsistent effects. In Figure 1d, the authors used the top single hits and tested pairwise combinations. The MIR1A and MIR15B combination consistently ranks among the strongest, outperforming the most single treatments and many other combinations. In Figure 1e, the images show that MIR1A/MIR15B inhibition increases Aurora B positive cardiomyocytes, indicating progression beyond S phase. This is important because many prior regeneration strategies induce DNA synthesis without cell division. This panel shows functional cell cycle completion. The authors had 4 key points in their research. The first is that combinatorial MIR1A/15B interference drives adult cardiomyocyte proliferation and maintenance of cardiac function in pathology. The second is that combinatorial MIR1A/15B interference specifically drives cardiomyocyte proliferation in vivo with minimal off-target effects. The third is that combinatorial MIR1A/15B interference enhances cardiomyocyte proliferation and function in human cardiac tissue mimetics. The fourth discusses mechanistic basis of LNA1A/15B function in cardiomyocyte proliferation induction.